Hello everyone, this is Sir Aris. Our topic would be for today is step functions. We will use it to deal with functions having jump discontinuities. Um, so the unit function or heaviside function is denoted by UC and defined by this equation where it UC of t is 0 for t less than c, the c here, and it's 1 for t greater than or equal to c. We are interested only in non-negative values of c because the Laplace transform involves values of t in the interval 0 to infinity. So that's why our c would be um, non-negative. The graph of um, y equals uc t would look like, so if you have uh, t versus y plot here. Let's change color. Okay, this is we start from c, or suppose this is our c. For t less than c, it's starting from 0. It would be 0, so it's just this line along t. But on c, it jumps to a value 1. Okay, so this doesn't include 1, but it jumps here and then extends towards infinity. The step function, so it's like a step function. You have a step here. Um, it can also be negative. For example, you want to plot 1 minus u c. Okay, this is c, this is 1. So from 0 to c, it would be uc is 0, so 1 minus 0 is 0. Okay, but it's excluding c, it jumps down to so 1 minus 1, that is 0 starting from here. Okay, so the step can also be negative. An example, let's consider uh, the graph of y equals ht, where ht is u pi t minus u pi 2 pi t. From the definition of uct, we can write this u pi t and u 2 pi t as, so u pi t, it's 0 for t less than pi and 1 for t greater than or equal to pi. For 2 pi t, u 2 pi t, that would be 0 for t less than 2 pi and 1 for t greater than or equal to 2 pi. So for h, our h now, which is given by u pi t minus u 2 pi t. We just combine these two, but take note there will be a total of 3 intervals. So from 0 to pi, from pi to 2 pi, and from 2 pi to infinity. So we have 3 intervals. Let's say the first interval is from for t between 0 and pi. We also have t between pi and 2 pi, not including 2 pi, so not including the right inequality. And for t greater than or equal to 2 pi. So between 0 to 2 pi, 0 to pi, you have u pi is 0, u2 pi is 0. So the answer is 0. Okay. Between pi to 2 pi, so greater than pi, this is 1. Between so less than 2 pi, this u2 pi is 0, so we have 1. And for 2t greater than or equal to 2 pi, this will be 1. This is also 1. You have 0. Okay, so in that case, if you want, so our goal is to sketch this. Suppose this is 1 here, and this is t. You have pi and 2 pi. So from 0 to pi, that would be 0. Okay, it jumps up to 1. From pi to 2 pi, excluding 2 pi. Okay, and then goes back down to 0. Okay, it's like a rectangular step function. Now let us consider this function. You have 1, 2, 3, 4 intervals. Express ft in terms of the unit step function. So the graph would look like, suppose this is our y-axis. The maximum value is 5, so let's have 5, 4, 3, 2, 1, 0, minus 1. Okay, and then here you have um, up to 9. So you say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, let's say 10. Let's just use this as 10 and then extend. 1, 2, 3, 4, 5, 6, 7, 8, and 9. From 0 to 4, the value of function is t. So that's up to here. Okay, not including 4. From 4 to 7 goes up to 5. Okay, so there would be a jump. That's from 5 to 7, excluding 7. From 7 to 9 becomes -1 here. So there's that jump. And then towards 9, excluding 9. And then at 9 starts from t equals 1 and then goes on towards infinity. If we consider only the interval 0 to 4, ft is simply equal to 2 here. But if we extend that for interval 0 to 7, ft now, instead of just having 2, it would jump up 3 steps. So you can use the unit function. So it jumps 3 steps starting from 4. Now for interval 0 to 9, we can still use that part up to 7, but from 7 it jumps down 1, 2, 3, 4, 5, 6 steps beginning from 7, and then finally for all t in the interval 0 to 8, to 8 to infinity, ft is equal to 2 plus 3 u4t minus 6 u7t plus, so from 9 it goes up 2 steps, u 2u9t. The Laplace transform of UC, it's actually easy to solve. You just take Laplace transform of UCT the usual way. So we integrate from 0 to infinity of u, or of e minus st u c t dt. Now UC starts from it's 0 up to t equals c. So the total integral is 0 up to t equal to c. So we can ignore that. We can start from time t, or variable t, from c to infinity. So you have e minus st u, or since u is a unit function, it's just 1, so we can leave it like this. If this is an uh, indefinite uh, integral, so you have this is an integral of improper integral, a definite integral with uh, one of the limit infinity. So one of the limits infinity, we can set a to infinity, c to a, e minus st dt. So this would be, take the limit as a approaches infinity of negative 1 over s e minus st, evaluated from c to a. So this would be negative 1 over s e to the minus s a minus e to the minus s c. Okay, for s positive, as a goes to infinity, this whole term becomes 0. So you have e minus cs over s for s greater than 0. For a given function f defined for t greater than or equal to 0, we consider the related function g given by this. It's 0 for t less than c, and it's ft minus c for t greater or equal to c. In terms of the unit step function, we can write gt as uc times ft minus c. This represents a translation of f, a distance c in the positive direction. If we create a plot of, let's say, f, suppose ft, y equals ft looks like this. Okay, this is our y, this is t. The translated, or our g, would be, so we start from c, this one. So at here, it is 0, but it jumps to the same value here. So it goes like this, and this would be your y equals gt, or uct ft minus c. Theorem: if fs is the Laplace transform of ft, it exists for s greater than a greater than or equal to 0. If c is a positive constant, then unit step function times f times t minus c, take the Laplace transform, is simply e minus cs Laplace transform of ft. If Laplace transform of ft is fs, then we can write it like this. By taking the inverse, we can then write uct ft minus c as inverse Laplace of this. To prove this, we compute the Laplace transform of uct ft minus c. Okay, so take uct, let me check, uct ft minus c. By definition, it's 0 to infinity of e minus st uct f t minus c. UCT is 0 for t less than c, so we can start with c and then remove this step function. Then we use, or using a change of variable, say we want to use psi, oops, equals t minus c. So the psi would be dt, and at t equals c, psi would be c minus c, or 0, so the limit here. So we have Laplace transform of uct ft minus c is equal to 0 to infinity, so c here we replace with 0, e minus s we replace t we replace with psi plus c, f psi d psi. We can factor out this sc, it's a constant, integral from 0 to infinity of e minus psi, or s psi s psi f psi d psi. This is simply the Laplace transform of f psi. You can also replace this dummy variable psi with t. So this is equal to f s. Hence, we write e minus sc fs. That's what we want to prove here. And taking the inverse, we get the second equation, equation 6.7. Example, if the function f is defined by ft sine t for t between 0 to pi over 4, but sine t plus cosine t minus pi over 4 for t greater or equal to pi over 4, we find the Laplace transform of ft. We can write ft as sine t, it always have sine t plus gt, where gt is 0, so there's no gt here for t less than pi over 4, but it would be cosine of t minus pi over 4 for t greater than or equal to pi over 4. So gt can be written as u pi over 4, starting from pi over 4, t times cosine of t minus pi over 4. So we now have Laplace transform of ft is Laplace transform of sine t plus Laplace transform of u pi over 4 t cosine of t minus pi over 4. Oops. Okay, so you have this sign and this. Laplace transform of sine t, that is simply 1 over s squared plus 1. And here, this would be from our theorem. This is e to the power of minus pi over 4 times s. Laplace transform of cosine of t. Okay, cosine of t, that is from here. This. And Laplace transform of cosine t, we can check our table. That's s divided by s squared plus 1. So finally, we can write Laplace transform of ft as 1 plus se minus pi s over 4 divided by s squared plus 1. Another example, find the inverse transform of fs equals 1 minus e to the minus 2s over s squared. So we can write ft, or the inverse Laplace transform, as the inverse Laplace transform of 1 minus e minus 2s over s squared, or 1 over s squared minus e to the minus 2s over s squared. And since Laplace transform is linear, this is L inverse of 1 s squared minus L inverse of e minus 2s over s squared. So using Laplace transform of t equal to 1 over s squared for s greater than 0, and theorem 6.3.1, is that 6.3.1? Yes, this one. The Laplace transform of e, or inverse Laplace transform of e minus cs of fs is u c t f t minus c. So in our case, we can write that as Laplace transform or inverse Laplace transform of e minus c s of 1 times 1 over s squared equal to u u c t t or f t minus c. F t minus c. Okay. S squared is our one for this case here. You have e minus 2s. This c here is our 2. The function is 1 over s squared. So we take, since we know that the inverse Laplace transform of 1 over s squared is t, you have a function that is just equal to t, and then we replace t with t minus c. So the inverse transform of fs is simply t for this part minus, for here you have u to t, c is 2, um, not to t but to t, times function of t replaced by replace t with t minus c, but the function is simply t. So t minus c, and that's it. Another theorem, if Fs is equal to L, exists for S greater than A greater than or equal to 0. If C is a constant, then the Laplace transform of ECT is equal to Fs minus C. For the proof, we evaluate the um, Laplace, hold on, the Laplace transform of ECTFT. So Laplace transform of ECTFT is, so take the integral from 0 to infinity of E minus ST, ECT, FT dt. Simply 0 to infinity of E to the minus S minus C T FT dt. If we set this as one variable, it's just equal to Laplace transform with kernel e to the minus that variable t, or a transform with kernel e to the minus that variable t, or we can simply, that is, we can set this also as a dummy variable, s minus c, similar to a Laplace transform where s is replaced by s minus c. From a previous theorem, theorem 6.1.2, this Laplace transform exists for s minus c greater than a, or cs is greater than a plus c. You can also take the inverse Laplace transform so that you get the second equation. Example, find the inverse transform of gs equals 1 over s squared minus 4s plus 5. We can write gs equals 1 over s squared minus 4s plus 5 as 1 over s squared minus 4s plus 4 plus 1. Or as 1 over s squared, or s minus 2 squared plus 1. So you see, we can change this into one single variable using, so what we, if you change this to one single variable, take note that we can use fs equal to 1 over s squared plus 1, whose Laplace transform is the Laplace transform of fs is sine t. We can call that our function ft. So we can also write fs minus 2 becomes s minus 2 squared plus 1. So gs can be written as fs minus 2. Okay. So if you want to use the theorem, inverse fs minus c equals ect ft. In our case, you have the Laplace inverse of g here, is equal to e to the c here is this number 2. So c is 2. So you have 2t. Ft is the sine t.